In today's lesson, we are going to be looking at trigonometry applications. So before we get into some trig applications, we want to first just kind of review the unit circle. Right, so the unit circle is the circle being used that has a radius r, and the radius and the coordinates of a point on the circle, so a point that is somewhere around or on the circumference of the circle, given by the values x, y, are related to the primary trig ratios. So we've looked at this unit circle before, right? We've looked at the r, the x, the y. We came up with equations for sine, cos, and tan, right? Using these coordinates on a Cartesian plane and a terminal arm, we came up with these different equations. Now, a unit circle is specific because a unit circle is the same idea, but it has a radius of 1. So when we include that radius of 1, we see that the ratios now become sine is equal to y, cosine is equal to x, and then tan is equal to y over x. Tan we're not really concerned about because when we're dealing with our sinusoidal functions for our sine or cosine waves, we're dealing with only sine or cosine. But when we look at sine theta and cos theta, when we're dealing with a unit circle, we realize, or we can see in these two parts here, that sine, again, like we said, refers to the y, or the vertical portion, and cos refers to x, or the horizontal portion. So for our trig ratios using the unit circle, the sine function graphs the relationship between an angle and the vertical displacement from the x-axis, so how high vertically we are from the x-axis, And for the cosine function, it graphs the relationship between the angle and the horizontal displacement from the y-axis. So the sine function is going to deal with the vertical, and cosine is going to deal with the horizontal. Now, in some cases, when we're looking at kind of like a sine function, this part doesn't really matter too much. But when we're dealing with certain scenarios and we're asked to graph about the vertical displacement compared to the horizontal, right, that would determine what type of function we're going to use. So let's look at an example looking at this type of idea of the horizontal and vertical displacement. Right, so you are in a car or a box or however you want to word it. You're in one of those carts for a Ferris wheel. The wheel has a radius of 8 and turns counterclockwise. Let the origin be at the center of the wheel, and then we're going to sketch the radius and basically where our car is located, and then graph that. Right, so we want to sketch a graph of the vertical displacement versus the angle of rotation for one complete rotation. So I'm going to use my Cartesian plane here from 0 to 360 to kind of look at this scenario. Right, so if I'm beginning my car is along the x-axis, and it's basically being stretched out from the radius. So if I have a radius of, we'll say 8, let's see if we can find, so 1, 2, 3, 4, 2, 3, 4, 5, 6, 7, 8. Good. So this is basically representing where my car is going to be located, right? If it is on a circle, or the Ferris wheel has a radius of 8, my car is going to start here. So this would be the point 8, 0. It's then going to move counterclockwise in this direction. It's not going to be the best circle. Counterclockwise in this direction, so then my next coordinate will be here, which will be at 0, 8, right? Because it's still 8, or a radius of 8. And then we're going to come around again counterclockwise to here. This will be my next portion, right? So this would be -8 and 0. And then lastly, it's going to come down, not lastly, but second last is going to come down here. We're going to come to the bottom for my Ferris wheel, so 0, -8, and then it's going to come back up to where we started. So we want to graph the vertical displacement of this of the car versus the angle of rotation. Right, so if I'm going to start at 0, right, what is the vertical displacement at 0 degrees? Well, we can see that it is 0. We are on the ground, right, so to speak. There is no vertical displacement from where we started. Now next, at 90, we're going to be up 8. 2, 4, 6, 8. So at 90, we are up at 8. And at 180, we're back at 0. At 270, we're at -8. And then 360, we're back up at 0. So this is what it's going to look like. Ooh, that is what our graph of the vertical displacement is going to look like. So a sine function, right? And we're looking at these values that I'm highlighting. Those are the values that we're looking at when we're dealing with the vertical displacement. Now for the horizontal displacement, it's going to be the exact same kind of graph or kind of diagram, right? We're going to start over here at 8, 0. We're going to go up to 0, 8. We're going to come down to -8, 0. We're going to go down to 0, -8. We're going to go counterclockwise. Right. Should be a nice complete circle, but in this case, obviously, my sketching is not great, but we get the idea. Now, for this one, we're dealing with the horizontal displacement. So if I'm looking at 0 degrees, what is the horizontal displacement? So these are going to be all of the x values that I'm highlighting here. So we're starting at 8 for our horizontal displacement. Then at 90, we're going to 0. At 180, we are going to -8. 270, we're back up at 0. And 360, we're at 8. So if I sketch that, quickly join my points, I get a cosine function. So again, cosine function representing the horizontal displacement and the sine function representing the vertical displacement. Now C says sketch the bottom or sketch a graph of the horizontal displacement versus the angle of rotation for one complete rotation if your car starts at the bottom of the wheel. So this is going to be a little bit different because it's still going to be the same graph. We're still going to have those same points. Right? -8, 0, 0, 8. Sorry, 8, 0. Oops, got these wrong. 0, -8, 8, 0, 0, 8, -8, 0. I have my graph, again, roughly sketching it, just so I get an idea. Right, but we are now going to start at the bottom. So this is where we are starting. So this is going to be our 0, essentially, because we are starting from this location. So there is no rotation yet, or no angle of rotation. Even though, yes, based off of the diagram, we're at 270, right? If we're starting at the bottom, technically that is our 0 mark. So at 0, our horizontal displacement is 0. At 90, our horizontal displacement, or if we move counterclockwise, the next segment is at 8. So we are up here. At 180, or again, the next segment, we are back at 0. then -8, and 0. So again, now we have a sine function. So taking a look at this, right, this is just an idea of how, from my horizontal displacement, if I go back 90 degrees, right, compared to the regular horizontal displacement, we can see that there is, that's how we kind of relate the sine and cosine function. Because if I was to go back and make an equation for all of these, right, for a sine function, stretch of 8, so I have y equals 8 sine x. Here, same thing, but a cosine function, so y equals 8 cos x. Down here, this would be y equals 8 sine x again, or y equals 8 cosine x. 8 cosine x minus 90, because we're starting 90 back. So again, just shows that relationship between sine and cosine, and how it's basically just a shift of 90 degrees. Next, we're going to look, instead of modeling with graphs, we're going to look at modeling with equations. Right? So we're going to take these scenarios and try to model them with periodic functions, or basically sinusoidal functions. Right? So a group of students is tracking a friend, John, who is riding a Ferris wheel. So again, another Ferris wheel, at least at the beginning. A lot of these questions might deal with a Ferris wheel because it has that kind of periodic idea where we're rotating or repeating values. Right, so John is riding a Ferris wheel. They know that John reaches the maximum height of 11 meters at 10 seconds, right, and then reaches the maximum height, or sorry, the minimum height of 1 meter at 55 seconds. We want to develop an equation of a sine and cosine function that models John's height above the ground. Now, looking at kind of a graph will help, right? If we can kind of graph this, then it might be easier to visualize our equation, right? So we know that John has a maximum height of 11 meters at 10 seconds. So I can graph that. And then a minimum height of 1 meter at 55 seconds. So down here. And then, so again, if I want to come up with my equation, I need my amplitude, my A value, right? A is my max minus the min divided by 2. So I have my max, I have my min, right? Because I'm told that from the scenario. So 11 minus 1 divided by 2 is 10 divided by 2, or 5. So I can use that if I wanted to, because if I know that my amplitude is 5, I can go down 5 or up 5, and that will bring me to my midline. That also tells me my C value. So C will equal my max minus the absolute value of A, or my amplitude. So 11 minus 5 equals 6, which we do have. Now, for the K value, we need to determine our K value. K is 360 divided by the period. We don't have the period yet, though. But if I'm going to be looking at this, right, whether I look at my sine or my cosine function, right, usually we have the minimum halfway between, right, or it's about half of the period between the minimum and the maximum, right? Regardless if we look at a sine wave or a cosine wave, the distance from the minimum to the maximum is going to be half the period. So what we can do is say, okay, well, if it's 10 to 55, right, is one or one period or half a period, right? So it's from 10 to, or from not 10, sorry, from 0 to 55, or from 10 to 55, right? Our next one should be another 45 from there. So that next one, right, if this is half, then the next one should be another 45, which brings us to here, or 100. Right? So from the maximum to the minimum should be about half your period. So I can go to my next one, or I can use that to help me determine what where the next maximum would be. And I can graph this now just roughly if I want. I'll do that in a second because I can figure out my k value. 360 divided by the period is going to equal 360 divided by my period. I can see now it goes from 10 to 100. So 10 or 100 minus 10, or 360 divided by 90, which equals 4. So I have my k value, which is 4. Now the only other thing now is I need my d value. Now looking at this function, if I was to roughly graph it, right, I might not know exactly where these other values are. However, I could look and say, okay, well, if I know that from the max to the min is half, right, then it touches 0 at halfway through that. So if this is 90, then halfway should be 45, or sorry, no, the period is 90, so half is 45. So half of that is 225. Okay, this is just going to get a little bit messy. So I'm just going to roughly sketch what my function looks like. Based off of that, there is one key d value that I can easily find, and that is going to be the d value for cosine, because I can easily see my maximum. So the d value for cosine is going to be that that horizontal displacement, or that horizontal movement from the y-axis to the first maximum. In this case, it is 10. And then the d value for sine, if we go back to our previous lesson, the d value for sine was the d value for cos minus 90 divided by the absolute value of k. So we have 10 minus 90 divided by 4, or 10 minus 22.5, which equals negative 12.5. So again, different ways we can come up with these values, right? But again, because we can't really see where sine is, we don't really see that. The cosine is easy to find, and then we can kind of reverse or go backwards to find our sine, or the horizontal shift for sine. Now I have enough information to come up with my equations, right? It's going to be the exact same thing for both sine and cosine. One is going to have they're just going to have two different horizontal shifts. So we'll do sine first. So y equals 5 sine 4x. Instead of minus 12.5, it would be plus, because of the negative 12.5. So minus a negative is positive for addition. So x plus 12.5, and then plus 6. For cosine, it's going to be the exact same thing, except y equals 5 cosine 4x minus 10 plus 6. So the exact same thing, except the d value is changing for sine and cosine. B is asking, what is John's height above the ground after 78 seconds? Right, so here, once we have a specific value, right, we could go to our graph and say, okay, where is roughly 78? Okay, 78 is roughly about here. Let's go up to see where we hit our graph, but we haven't drawn our graph accurately anyways. We've only sketched it, so that doesn't help. But we do have an equation, right? And it doesn't really matter which one we use. I'm going to use the cosine one though, only because I'm very certain, or I'm extremely confident that my horizontal shift for cosine is accurate, because that is the value that I found, or that's the value that I could easily see. Now, you could use, or technically, if both functions are correct, you could use either one and get the same answer. So y equals 5 times cosine of 4 times x minus 10 plus 6. Instead of x, I'm going to write in 78, because it's 78 seconds is telling us that x equals 78. So 5 times cosine times 4 times 78 minus 10 plus 6. Here we just have to be careful, make sure we're using BEDMAS. We should end up with 5 times cosine of 272 plus 6. We get y equals 6.2 meters. Right, so just make sure we're doing BEDMAS, brackets, then multiplication, but we have brackets within brackets, and then do our cosine, then multiplication, and then add our 6. The next example, right? So we're looking at a skyscraper, and skyscrapers sway with or in high wind conditions. In one case, at t equals 2 seconds, the top floor of a building swayed 30 centimeters to the left, or negative 30 centimeters, and at t equals 12 seconds, the top floor swayed 30 centimeters to the right of its starting position. Right? What is the equation of a cosine function that describes the motion of the building in terms of time? And then B, we're going to do the same thing, but for cosine. So this is very similar to the last one, right? We do have our maximum and minimum values. So 30 centimeters to the left, or negative 30 and plus 30. And then we have the times that it occurs at. So start with A. So A equals our max minus min divided by 2, or negative 30 minus positive 30 is most likely going to be our maximum. So plus 30 minus negative 30 divided by 2 equals 60 divided by 2, or 30. So I have my A value, or we have the A value. C, I can do my max minus the absolute value of A, or 30 minus 30, which equals 0. My K value is going to equal 360 divided by the period. So 360 divided by, now the period, we don't really know, it doesn't really say. However, we do know that going from, we just roughly sketch it, from the maximum to the minimum, right? If I kind of sketch it, whether it's a sine or cosine, right? From the maximum to the minimum will be half our period. Let's do half p. So if it is going from 2 to 12, that is a distance of 10. If that represents half the period, then that means that a full period is going to be 20. So 360 divided by 20 equals 18. Last but not least, we need our D value for the cosine. Now this one is a little bit more straightforward. Even though we don't have it, right, sometimes a visual might help. So let's just kind of blow this one up a bit. If I'm looking for the D value for cosine, I'm looking for the horizontal distance it takes to get to this maximum. I do know that maximum occurs after 2 seconds, after 12 seconds. Oops, this is kind of reversed. Maybe something like this. We know it's going to take 12 seconds to get to this maximum, which is our d cosine, or horizontal shift for cosine. So that is going to be 12. Now I have enough information. I have all my variables. So y equals 30 cosine times 18. Not 30 cosine. 30 times 18 cos x minus 12. And there's no plus or minus. So that is our cosine function for this situation. Now for for the sine function, it is going to be the exact same thing. Y equals 30, 18 times sine x, and we're going to have a different d value. So that we have to determine. So d sine is going to equal d cosine minus 90 divided by the absolute value of k. So we have 12 minus 90 divided by 18. 12 minus 5 equals 7. So that means the horizontal shift for our sine function will be 7. So x minus 7. So that is our equation of a sine function that models this. Sorry, not 18. Ooh, been writing these ones a little bit off. 30 cosine 18 x minus 12. And then this one should be 30 sine 18 x minus 7. There we go. It's getting them into the right spots. So just kind of put my k value in the wrong spot. But that would be our sine and cosine function for this scenario with the skyscrapers swaying left to right. Last example, the height of the tide on a given day at t hours is modeled by, we don't have an equation here, but let's put in, it was going to be modeled by h at t is equal to 5 sine 5 sine 30 t minus 5 plus 7. So this is going to be our equation. We want to find the max and min values for the height of the depth of water. So different ways we could do it. We could go through and just kind of roughly sketch out this graph because we do have the function. We could also think about, okay, well, my C value is my midline. So at 7, I have my midline. That I do have an amplitude of 5, right? So that tells me that I have an amplitude of 5. So that tells me where my max and min should be in relation to this. We also do know that our maximum is equal to our C value plus the absolute value of A. Or in this case, our C value is 7 plus 5 gives us 12. And then for the minimum value, it's the C value minus the absolute value of A, or 7 minus 5, or 2. So that means the maximum height and the minimum height is going to be 12 and 2, respectively. Next, we want to figure out what time is high tide and what time is low tide. So we have to think about when these different times are going to occur. Now, we do know that the first rising midline is going to be at 5. Right? And we get that from the equation of t minus 5. So our first rising midline is d for our d sine is equal to 5. Right. So if I were to basically, if I look at 5, my graph is rising upwards. I know that it's rising upwards because of that d5, or that horizontal shift of 5. So if I want to figure out now where my first high tide is, or what the high tide time is, I'm going to look for my d cosine. So the first, which would be the first maximum. And that is going to be 5 plus 90 divided by k, or the absolute value of k, or 5 plus 90 divided by 30, which I'm just getting that from my equation, right? The k value is 30, or 5 plus 3, or 8. So that means at 8, I have a maximum at 12. And I do know that I'm going to have my midline rising at 5. So I know roughly my graph is going to look something like this. So if it was rising at 5 and goes to 8, then that means another 3 at 11, it will be coming back down. You could then say another 3, and it's going to end up at the minimum, so 14, so it's going to end up down here. Right, so using that periodic behavior, right, so every 3 should be where it kind of either hits a midline or hits a minimum or a maximum. So 17, then it should be coming back up, and then 20, it should be hitting our maximum. So that's the nice thing about periodic behavior, is that you can kind of see when it starts to repeat. What time is low tide, right? Or I guess technically we still haven't figured out all of high tide, because we just saw here, we're just going through and finishing our graph, that high tide can occur at multiple parts, right? We also know, or can determine, our period. So period is going to equal 360 divided by k, or 360 divided by 30, which equals 12. So if one high tide is 8 or 8 a.m., it's at 8 a.m. and let's say 8 p.m. Or if I added 12 to 8, that's 20. So think of a 24-hour clock, 20 or 2 or at 200 or at 200 hours. I'm not sure. I don't really remember how to pronounce the time. 200 hours. Because not 2400 hours. 200 hours. The time would be 8 p.m. So, or you think 12 hours from 8 a.m. is 12 p.m. So that is your high tide. Now for low tide, it's going to be a little bit different. Right? So if we know that the first rising midline is at 5, then again, in terms of kind of moving things by every quarter, or in terms of like 90 degrees, right? If we go back to our parent functions, that's when everything kind of occurred, right? Every 90 degrees, we were either at a midline or moving to, or at a maximum or a minimum. So if our first rising midline is 5, so again, that horizontal shift of 5, use a different color. So we had d sine equals 5. That means, can't really say, it's not really the d cosine, but if I do 5 minus 90 divided by the absolute value of k, or 5 minus 90 divided by 30, we get 2. And again, with a period being 360 divided by k, or 360 divided by 30, or 12, that means every 12 hours. So therefore, low tide is at 2 a.m. And you could either think of 1400 hours or 2 p.m. So different ways to think about it, but if we're looking for a max and min and we don't quite really know them, right? Again, those values should occur at kind of like every quarter, right? Or not max and min specifically, but those kind of key points, right? Either the zero, the max, or zero, and then in the min, right? It goes every quarter that we get to those values. So what is the depth of water at 8 or at 9 a.m.? So this is just using our function. H at 9 is equal to 5 sine 30 times 9 minus 5 plus 7. So we get 5 times sine of 120, plus 7, or we get 11.3 meters. Right, so this one, just plugging the value in into the function and solving. So in this lesson is just looking at some of the trig applications, just understanding how a periodic function can look graphically, how we can take a scenario that models periodic behavior, come up with an equation for it, or graph that, or graph it if needed, but mostly coming up with an equation to model that scenario, and then using the model if needed to make predictions or estimations of what one of the variables may be.